Consensus in distributed systems. Consensus is the process by which multiple nodes in a distributed system agree on a single value or decision. Each node operates independently and may have different information or system states. They communicate by sending messages, which can sometimes be delayed or lost. Consensus mechanisms ensure that all non-faulty nodes eventually agree on the same decision. This is crucial for maintaining consistency and reliability in decentralized systems. Popular algorithms like Paxos and Raft are used to achieve this agreement. For example, in a distributed database, multiple servers must agree on the order of transactions. Even if one server fails or messages are delayed, a consensus algorithm ensures that all active servers store the same data in the same order. Consensus is essential in distributed systems for several reasons. First, it helps maintain consistency by ensuring all nodes agree on the same data or decisions, preventing conflicting system states. Second, it allows the system to handle node failures. Even if some nodes crash or become unreachable, the remaining nodes can continue to operate correctly. Third, it supports decentralization. In systems without a central controller, consensus enables independent nodes to make coordinated decisions. Fourth, it prevents conflicting decisions, which could otherwise cause errors or data corruption. Finally, consensus ensures system reliability, improving the fault tolerance and overall dependability of distributed applications. 1. Paxos algorithm, CFT, diagram explanation. Proposer, top. The proposer is a node that starts the consensus process by suggesting a value to be agreed upon. Proposer, bottom. Multiple proposers can exist, and each proposer may independently try to propose a value. Acceptors, top. Acceptors receive proposal requests from proposers and decide whether to accept them based on proposal numbers. Acceptors, middle. Each acceptor responds only if the proposal number is higher than any proposal it has already seen. Acceptors, bottom. A value is considered accepted only when a majority of acceptors agree on the same proposal. Learner. The learner collects information from acceptors and learns the final chosen value once consensus is reached. Paxos is a distributed consensus algorithm used in distributed systems to make sure that multiple nodes agree on a single value. It is designed to work correctly even when some nodes crash or when messages are delayed in the network. Paxos follows a crash fault tolerance model, which means nodes may fail by stopping their execution, but they never send wrong or malicious messages. The main goal of Paxos is to guarantee safety and consistency, ensuring that no two correct nodes ever decide on different values. To achieve consensus, Paxos uses a majority quorum mechanism. This means more than half of the nodes must agree on a value before it is chosen. Because only a majority is required, the system can continue functioning correctly even if some nodes fail or become unavailable. Paxos works using three main roles: the proposer, the acceptor, and the learner. The proposer is responsible for initiating the consensus process by suggesting a value. It starts by sending a prepare request along with a unique proposal number to all acceptors. Each acceptor checks whether the received proposal number is higher than any proposal number it has seen before. If it is higher, the acceptor responds positively to the proposer. After receiving responses from a majority of acceptors, the proposer sends an accept request containing the proposed value. When a majority of acceptors accept this proposal, the value is considered chosen. Finally, the chosen value is communicated to all learners, so every learner knows the final agreed value. Paxos is a crash fault-tolerant algorithm, meaning it can handle node failures where nodes stop working but do not behave maliciously. It uses a majority quorum for decision-making, which allows the system to continue operating as long as more than half of the nodes are available. Paxos guarantees safety and consistency by ensuring that all correct nodes agree on the same value and never reach conflicting decisions. It also works correctly even in the presence of network delays and node crashes. One major advantage of Paxos is its strong consistency guarantee, making it suitable for critical distributed systems. It provides reliable consensus even when some nodes fail. However, Paxos is complex to understand and difficult to implement correctly. Another disadvantage is that performance can degrade when there are frequent leader or proposer changes, as this increases coordination overhead. Raft consensus algorithm, diagram explanation. Client. The client sends a request containing an operation or message to the Raft system. Message, X. The client always sends its request only to the leader node. Server, leader. The leader is responsible for handling client requests and coordinating consensus. Server, follower, top. Followers receive log entries from the leader and replicate them locally. Server, follower, right. Each follower acknowledges the received log entry back to the leader. Server, follower, bottom. Followers do not communicate with the client directly, they only follow the leader's instructions. Reply, X. Once a majority of followers acknowledge the entry, the leader commits it and sends a reply back to the client. Raft consensus algorithm. Raft is a distributed consensus algorithm designed to be simple and easy to understand. It allows multiple nodes in a distributed system to agree on a single consistent state, even when some nodes crash during operation. Raft follows a crash fault tolerance model, meaning nodes may fail by crashing but they do not behave maliciously. To make consensus easier to understand and implement, Raft divides the problem into three main components: leader election, log replication, and safety. In Raft, a single leader is elected, and this leader is responsible for managing log replication across all follower nodes. By having one leader coordinate the system, Raft simplifies communication and coordination compared to more complex algorithms like Paxos. Raft operates using three states called the leader state, follower state, and candidate state. Initially, all nodes in the system start in the follower state. A follower remains in this state as long as it receives regular heartbeat messages from a leader. If a follower stops receiving heartbeats for a certain period of time, it transitions into the candidate state and starts a leader election. During the election, nodes vote, and the candidate that receives a majority of votes becomes the leader. Once elected, the leader handles all client requests by appending them to its log. The leader then replicates these log entries to all follower nodes. When a majority of nodes acknowledge the replicated entry, the leader commits the entry and informs the followers to apply the change, ensuring consistency across the system. Raft uses a leader-based consensus mechanism, where a single leader coordinates all decision-making in the system. It requires a majority quorum for both leader elections and log commit operations, ensuring that decisions are reliable. Raft provides strong consistency and fault tolerance by making sure all nodes eventually agree on the same state even if some nodes crash. It also has a clear separation of roles and responsibilities, which makes the algorithm easier to understand and reason about. One major advantage of Raft is that it is easier to understand and implement compared to Paxos. The presence of a single leader also results in predictable system behavior. However, the leader can become a performance bottleneck when the system handles a high number of client requests. Another disadvantage is that if the leader fails, the system experiences temporary unavailability while a new leader is elected. Byzantine fault tolerance is a property of distributed systems that allows them to reach consensus and continue operating correctly even when some nodes behave arbitrarily. These behaviors can include system failures, malicious actions, or sending incorrect or misleading information. Unlike crash fault tolerance, Byzantine fault tolerance handles situations where nodes may act unpredictably or intentionally malicious. It assumes that some nodes can send false or conflicting messages, either due to software bugs or deliberate attacks. To tolerate Byzantine faulty nodes, a Byzantine fault tolerance system typically requires at least 3 F+1 nodes. This extra number of nodes ensures that the correct nodes can outvote the faulty ones and still reach a safe and consistent consensus. In a Byzantine fault-tolerant consensus system, nodes exchange messages with each other in multiple rounds to agree on a single value. During each round, every node carefully validates the messages it receives from other nodes to check their correctness. The system follows a strict voting process to prevent faulty or malicious behavior from affecting the outcome. Consensus is reached only when a sufficient number of nodes agree on the same value. Typically, at least 2F plus 1 honest nodes must agree, where F represents the maximum number of Byzantine faulty nodes. This requirement ensures that malicious or faulty nodes cannot override the correct decision and the final agreed value remains safe and consistent. Byzantine fault tolerance can handle both crash faults and malicious faults, making it suitable for highly unreliable environments. It requires strong message authentication and verification so that nodes can detect false or tampered messages. BFT ensures safety and consistency even when some nodes behave incorrectly or maliciously. Because of these properties, it is well suited for untrusted or adversarial environments such as public distributed systems. One major advantage of BFT is its high level of fault tolerance and security. It continues to work correctly even when some nodes intentionally behave in a malicious manner. However, BFT algorithms suffer from high communication overhead due to frequent message exchanges between nodes. They are also more complex and resource-intensive compared to crash fault-tolerant algorithms. Distributed consensus faces several challenges. Node failures can make agreement harder when some nodes crash. Network delays and partitions may cause messages to arrive late or out of order, leading to inconsistencies. Malicious behavior is a risk in some systems, where nodes act unpredictably or send false data. Scalability becomes harder as more nodes join the network. Finally, systems must balance consistency and availability, and designing consensus algorithms can be complex and error-prone. Consensus is essential in many distributed systems to maintain reliability and consistency. In distributed databases, it ensures all replicas store the same data, like in Google Spanner or MongoDB. In blockchains, consensus keeps a consistent ledger of transactions across all nodes without a central authority, as in Bitcoin and Ethereum. It guarantees that replicated state machines execute operations in the same order across servers. In cloud storage, consensus coordinates multiple storage nodes to replicate data reliably. It's also used for leader election, selecting a node to coordinate tasks, as seen in Raft and ZooKeeper.